All right, so today we're going to tackle a classic coding problem. And on the surface, it seems pretty simple, but trust me, it unlocks a really powerful way of thinking. A secret, really, to making things incredibly fast. This is the kind of strategy that powers, well, basically everything, from your search engine to the massive databases that run the world.
So let me just ask you this. How would you find one specific word in a giant, heavy dictionary with, I don't know, a million words? Where do you even start? I'm gonna bet you wouldn't start at the very first page, right?
Exactly. You don't start at A and just flip every single page. Your brain, your intuition, it tells you to crack it open somewhere near the middle. You glance at the page, see if your word comes before or after it, and bam! In one single move, you've just cut the entire problem in half. That simple idea, that's the key to everything we're about to talk about. Okay, so let's take that dictionary idea and turn it into a formal challenge, with a very specific set of rules we have to follow. This is where the real fun starts. The problem is called search insert position. Here's the setup. We get a list of numbers that's already sorted, and we get a target value. And our goal has two parts. First, if our target is already in the list, we just have to say where it is, what's its index. But if it's not in the list, then we have to figure out where it should go to keep the whole thing sorted. Let's look at a super simple example. Say our list is 1, 3, 5, 6, and our target is 5. Well, that's pretty easy. The number 5 is right there, sitting at index 2. So far, so good. But what if the target is 2? See, 2 isn't in our list. So the question becomes, where would it go? Well, it would have to slot in right between the 1 and the 3, which is index 1. And that's the other half of this puzzle. And this is the big one, the most important rule. This might look like some scary math notation, but what O of log n really means is you have to be unbelievably fast. You can't just go through the list one by one. You have to be way, way smarter than that. So this is the whole point right here, the difference between these two. A linear search, that's O of n, is our start at page 1 method. If you have a million items, it could take you a million steps. But a logarithmic search, our O log n, that's our split in the middle strategy. And get this, for a million items, it takes about 20 steps. Not 20,000, just 20. That is the kind of power we need to unlock here. And this amazing strategy has a name, and it's a great one: divide and conquer. It's all about making the problem smaller and smaller and smaller again and again until it's just too simple to possibly get wrong. The logic behind it is just beautiful in its simplicity. Step 1, you find the middle. Step 2, you compare your target to whatever's in the middle. Step 3, and this is the key, you just throw away the entire half of the list where your target can't possibly be. And finally, step 4, you just repeat. You do the exact same thing on the tiny piece that's left over. Okay, so the high-level idea makes sense, but how does a computer actually throw away half the data? Let's trace the code and see exactly how it works. We'll use our second example, where the list is 1, 3, 5, 6, and we're looking for the number 2. So we start by setting up 2 pointers, basically just bookmarks to keep track of our search area. We'll call them S for start, which begins at index 0, and E for end, which begins at the last index, 3. At this moment, our search space is the whole array. Now, the first thing we do inside our loop is find the dead center of our search space. So we add the start and end indices, 0 plus 3, and divide by 2. That gives us 1. So our middle pointer, mid, is now pointing to index 1. Time to compare. The number at our middle index is 3. So the code asks, is 3 greater than our target 2? And yes, it is. That one little comparison tells us something huge. Our target can only be in the half of the array to the left of the middle. So, to officially discard that entire right half, the code just moves our end pointer, E, to be mid minus 1. So our new end is now index 0. And now we start the loop all over again. But look at our pointers now. S is still at 0, and our new E is also at 0. In just one single step, our search space has shrunk from 4 items all the way down to just 1. So we just repeat the process. We calculate the new middle. 0 plus 0 divided by 2 is, well, 0. So our mid-pointer now points to index 0. And it's time for our next comparison. The value at our new middle, index 0, is 1. So is 1 less than our target? 2. Yes, it is. And that tells us that our insertion point must be somewhere to the right of this position. So the code takes action again. This time, to get rid of that left side, it moves the start pointer, S, to be one spot greater than the middle. Our new S is now 1. And here it is, the crucial moment. The code checks its mean condition to keep going. Is S less than or equal to E? Well, S is now 1 and E is 0. That is false. The pointers have actually crossed each other. The search is over. The loop stops. So what happens when the loop ends? This is the most brilliant, most elegant part of the whole solution. The very last instruction is just return the value of the start pointer, S. And what's the value of S? It's 1, which is exactly the index where the number 2 should be inserted. The algorithm worked perfectly. It didn't find the number, it found the answer by just systematically eliminating every single place it couldn't possibly be. Okay, let's just zoom out for a second and appreciate why this isn't just some clever little coding trick. This is a fundamental, game-changing principle in computer science. This right here is the magic of O log n. Just look at this chart. For a small list, yeah, the search time is tiny. But for a massive list with over 1 million items, the search time barely even moves. It's still incredibly low. This insane efficiency is why your phone can find a contact instantly, or how a database can find one record out of billions in a blink. It's an almost flat curve, which is just incredible. So, what are the big things to take away from this? First, if your data is sorted, you basically have a superpower. You should always be looking for ways to use it. Second, divide and conquer isn't just for code, you know? It's a powerful mental model for breaking down any huge problem. Third, that O of log n efficiency, that's the engine that makes our modern digital world even possible. And finally, just remember the elegance of those pointers, S and E, just systematically cornering the answer until there's literally nowhere left for it to hide. And that leaves us with one last thought. This whole idea of splitting a problem in half, it doesn't just apply to sorted lists of numbers. So the real question is, what other big, complex problems, maybe in your work, maybe in your life, could be made so much simpler just by finding the middle and throwing half of the problem away?